Hello, we're going to talk about vibrating membranes. And we start with the wave equation. So how are we going to model this? We're going to take a function, u, from some domain, and then time into the real numbers, which will satisfy the following equation. So it's the wave equation that we've seen before, like this, where, again, Laplacian is given by this, and we'll have boundary values that u of x, y at time t will be equal to 0 for all x, y, which are in the boundary of the region, like this. And we have initial condition that at time 0, ux, y is some function f of xy, and the time is some other function g of xy, like this. So this is very similar to the vibrating string equation or vibrating string problem, but now we have 2 dimensions, and we're going to have to adapt the machine that we've been working on to actually deal with this case. So how do we begin? So solution to this equation, problem. First thing we want to do is do separation of variables, and the general strategy will be kind of similar. We're going to separate variables. We're going to isolate off an eigenvalue, eigenvector, or eigenfunction problem. We're going to solve the eigenfunction problem. We're going to use those eigenvalues, eigenfunctions to actually build up a general solution. Okay, so it's extremely analogous. It's the same set of ideas that we've been using over and over again, but now we're doing this in higher dimensions. So let's just give it a go. So try separation of variables. So let us write u, x, y, t as the product of these functions phi, x, y, and h of t. Then what happens to our ODE, or to our PDE? Let's call this PDE star. So star becomes the following thing. It becomes h double prime of t, phi of x, y, is equal to h of t, Laplacian, phi of x, y. Okay, so let's divide. Put things on the same side. I'm missing a c squared right here. Right. So separating things off, h double prime over c h of t is equal to Laplacian phi of x, y, phi of x, y. This is a function in t, this is a function in xy. The only way these things can be equal is if they are equal to some number, which we're going to write as minus lambda. And we're writing minus lambda because we anticipate that lambda will have to be positive. Because if lambda is not positive, then the thing that will solve this will have to be something which is going to be either a linear combination of hyperbolic sine or hyperbolic cosine. And in either case, we're going to have things that blow up to infinity as time increases. And that's not what we expect the solution to be. We don't expect the actual solution to this to be able to just blow off to infinity. We expect it to remain bounded. I mean, this is a model for taking as a model for a drum. Simply, we're taking some kind of a membrane that we're we're pulling, we're stretching it around some domain, we're fixing it to the boundary, and our experience of these situations is that when we hit it, it doesn't vibrate to the point of just lifting higher and higher and higher off to infinity, right? So this is a reasonable assumption. So for physical reasons, we can also deduce this later from the Rayleigh principle or the Rayleigh quotient, but for our purposes, it's enough to just say for physical reasons. We expect bigger than 0. So let L of phi be the Laplacian, okay? And what we are looking for is to solve the following thing. L of phi is equal to minus lambda of phi for phi. It needs to be twice differentiable, defined on omega, and we insist that it is 0 on the boundary. Okay, so this is a linear space, right? And this is a linear operator. So we are exactly in the scenario of finding eigenvalues and eigenfunctions for a linear operator in an infinite dimensional space, exactly as we have done before, but now these are functions in 2 dimensions. Okay, so we are going to initially solve this with the special case of when omega is a rectangle. So we'll take this kind of rectangle, okay? And we're gonna try and solve this, find our collection of eigenvalues, eigenvectors, and then from that build our solution U as out of them. Okay, that's what's coming up. Okay, so omega again is this rectangle. And we are trying to solve this eigenvalue problem with this is our space. Okay, so the way we're going to do this is again to use this method of separation of variables. So try separation of variables again. And so let's take phi of xy to be, say, f of x, g of y. And let's see what this thing looks like. So let's call this thing. I should also say that L of phi, remind you again, is Laplacian. So if we have the Laplacian like this, then what's our equation? We are going to have this thing. Oops, this is y. Like this is equal to minus lambda f of x g of y. Yeah? All right, so let us divide through by f and g, and this gives us that okay, let's put one of those things on the other side. So like this, yeah. And the only way this can be true is if this thing doesn't depend on x and this thing doesn't depend on y, right? In other words, this has to be constant and this has to be constant. Yeah? So this implies that not both ways, well actually both ways, but I only care about one way, that f prime prime of x over f of x is equal to this thing is equal to some number mu, and I'm going to let mu be minus the time being, like this. Okay. And we also want to have that the boundary conditions are satisfied. So the boundary conditions are that the functions are 0 on the boundary, and in terms of f and g, that means that f of 0 has to equal to f of L, which is equal to 0, and g of 0 equals g of h, which is equal to 0. Okay, so from that, I can see that I want to have I want to have mu be a positive number, because again, if not, then the solution would be f would have to be some combination of hyperbolic sine, hyperbolic cosine, and so let's remind ourselves of the graph of hyperbolic sine, so and hyperbolic cosine. So hyperbolic cosine of x equals e to the x plus e to the minus x over 2, right? So it just blows up. Hyperbolic sine is equal to e to the x minus e to the minus x over 2. So it is 0 at 0, but then it just blows up, right? So we can't, with either of these functions, create something which is going to be 0 on the boundary. So we on both ends of the boundary. So we are going to make the assumption that mu is actually a positive number, and therefore we are in the territory of sines and cosines. Okay, cool. So this being our situation, now we are really in familiar territory. So looking at f, so f has to be the form over here, f n of x is going to be sine pi nx over L, right? And this implies that mu, therefore, is going to be pi n over L squared. Yeah? For any n belonging to natural numbers. Yeah? And once we have that, what we're going to have for g is that g is going to have to satisfy the following. To equal to minus lambda plus pi n over L squared, like this. Yeah? So the important point is that this thing is a constant, right? Yeah? And we have that g of 0 equals g of h is equal to 0. And then again, we know what the solutions have to be. We have to have g of y is equal to sine of m pi y over h. Yeah? And then working with this, we have g double prime of y. As we know, g double prime of y is going to be m pi or minus m pi h squared g, and so finally this gives us that since this thing is equal to this, it's got to be a constant. The constant has to be this thing. So we have that minus m pi h squared is equal to minus lambda plus pi n over L squared. Unwrapping that, we have that lambda is equal to m pi over h squared plus n pi over L squared, like this. Yeah? So our original lambda in this eigenvalue problem has to be of this form for integers m and n. Yeah? And we have that this thing, let's call it actually m, depending on m, like this. And we now have a whole family of eigenfunctions parameterized by m and n, which are going to be given by this sign of pi x, or let's put the n in here, y. Okay. Cool. So these guys, when we apply Laplace into it, working backwards through all this stuff, these guys will indeed satisfy this equation, elegant as Laplacian, and the eigenvalue we will get will be given by this thing. Okay. So we have a whole family of eigenvalues and a whole family of eigenfunctions. The difference being now that we have two indices, m and n, which we run over as opposed to one index when we did the vibrating string. You know? Nevertheless, this is morally the same thing, because whether we have two indices running from 1 to infinity, m and n, or just one, we still have just a countable collection. What we need to get the machine to work is the same kind of properties. We need these functions, these eigenfunctions, span the space, and what would be really convenient would be as if they're orthogonal. And in this particular case, for this family of eigenfunctions, that's what we have. More generally, as we'll see, that is not automatically true. So one of the features that is different, and we'll see this later, is that we'll have the same eigenvalue with different eigenfunctions. So in the one-dimensional case, each eigenfunction was in the general Sturm-Liouville theory, we had each eigenfunction was associated to an individual eigenvector. Start again. Each eigenfunction was associated to an individual eigenvalue, and then orthogonality followed rather easily from that property just by the fact that the operator was self-adjoint. In this case, it's not true. We're going to have actual non-trivial eigenspaces. We're going to have, for certain eigenvalues, there'll be a non-trivial eigenspace, and inside that eigenspace, we can collect an orthogonal collection of eigenvectors. We'll have to work a little bit harder to get our orthogonal collection of eigenvectors in the most general situation. However, in this case, it just falls out for free, because for any index m and n, these guys actually will be orthogonal in the sense that when we integrate over the rectangle, the product of any of these two kinds of functions for different indices, this integral would be 0. And that will follow in very similar ways. The way we know it's 0 just in a real line, we'll just break up the integral using Fubini, we'll integrate on lines, and that will be true. But in general, it's not so trivial. It's not handed to us as easily as in the one-dimensional case. Okay, let us talk about this a bit more on the next board. So what we've learned is that these functions phi, m, n, x, y, is sine of n pi x over L, sine of m pi y over h. These guys solve our eigenfunction, eigenvalue problem that Laplacian phi m n is equal to minus n pi over L squared plus m pi over L squared phi m n. Okay. It is a fact, and we'll talk about it later, that this space of functions spans the space of functions defined from the rectangle into the real numbers. Okay. And therefore, by principle of superposition, we can attempt to build a general solution with these kind of building blocks, right? So these are the guys that satisfy the eigenvalue problem. We also have to solve the equation in time, right? So with respect to time, I think we called it h. So we have h double prime of t has to equal to minus lambda of h of t, where lambda was an eigenvalue. In these cases, our eigenvalues are this, so our h of m n of t will have to be this function. So what are the boundary values of h? There are none. Simply h is the time function. We would like it to be non-zero at time is equal to 0. And we also like the derivative to be non-zero at time equals 0. But that is the only criteria. So we can solve this with a linear combination like this. Let's call it A, M, N, M. Of cosine of the square root of this number, lambda n, which is this number. I'll define it explicitly in a second. Okay, where lambda m n is this number plus m pi over L squared, yeah? And by superposition, we have that general solution can be given by divided by this infinite sum, so the sum over all indices m n from 1 to infinity. We're going to start from 1 because if either of these guys is 0, then it's just the 0 solution. It doesn't do anything. And then we're going to have these guys, right? So let's write it like this. A m n cosine n of t plus b m n sine square root of lambda m n. Oh, doesn't mean these things are symmetrical. N m of t like this. These things multiplied by sine of pi nx over L sine of pi my over L. So ignoring all issues of convergence of this series, formally this thing will solve our heat equation, except that I've dropped the c right? So there should have been a c squared here, and therefore I want the c right here, like this, right? So this thing will formally solve the wave equation on a rectangle. It will model the vibration of a vibrating membrane. The issue is, can we make this thing for the correct choices of coefficients a, n, m, and b, n, m? Can we make it agree with the initial data, the initial conditions? So let's describe this general solution as u, x, y of t. Okay, let's define it like this. Then note that u, x, y of 0 just becomes this thing, the sum from m n equals 1 to infinity, a, m, n of these guys. Actually, let me just save notation. Let me just write it. Okay. And if we take the derivative with respect to time, then it's going to turn this thing into a sine, so that when we put t equals 0, it just vanishes. This will now become a cosine, but we'll get this extra factor of c square root of lambda m n, right? And okay, cool. So if these guys do indeed span the space of functions from the rectangle to the real numbers, then there should be coefficients a, n, m we can find that will actually make this agree with the initial data. So we want this to be equal to f of x, y. And same reasoning, we want this to be equal to g of x, y. And we can certainly do this because we can find coefficients b, m, m, such that no matter what these numbers are, we can make this representation be true, right? So long, again, as we have that these things span the space of functions, ignoring, as always, all issues of convergence. So we're in good shape, okay? But we need this fact. And actually, to calculate the coefficients, we also would like to have orthogonality. So let's state the general Sturm-Liouville type theorem that we are going to use to complete the fact that this is a solution. So general Sturm-Liouville. So now we're doing this in 2 dimensions, or more generally in higher dimensions. And the analogous Sturm-Liouville equation is the following. We're going to take the divergence of some function p, scalar valued function p defined from R2 in this case, or Rn in general, times the gradient of a function, let's call it phi, like this, and then plus some other function, let's say q times phi, plus lambda sigma times phi is equal to 0, okay? Where p, q, and sigma are non-zero, are non-constant functions. and we're going to expect this thing to be bigger than 0, like this. And we're going to have some kind of boundary conditions which most generally we could express as follows, that say a of phi plus b of the gradient of phi times the normal to the outward, to the boundary, so this is a outward pointing unit normal, is equal to 0. Okay, this is our replacement for the general boundary conditions in one dimension, which would just be a plus b times the derivative. Derivative would just be a number. Now the derivative is a vector, so we have to specify what we mean, and what we mean is the vector dot product with the normal equaling to 0. Okay, so these are the general boundary values, and again, this is a eigenvalue, eigenvector, or eigenfunction problem in the following sense, that if we define L of phi to equal to sigma to the minus 1 of the divergence of P gradient phi plus U plus Q times phi, then we're looking for solutions to this problem right here, which is again an eigenfunction, eigenvalue problem, and you can check for yourself. It's an easy thing to check that this is a nice linear operator. Okay, this is nicely linear on the space of functions. Okay. So this is entirely the high dimensional analog of the Sturm maneuver we did in one dimension, except, as I've mentioned before, we have slightly weaker properties that we don't necessarily have orthogonality of the eigenfunctions, because eigenfunctions can have the same eigenvalue, so it's actually a non-trivial eigenspace. Okay, I erase the board, and then we'll go into some more detail on this. Here's a theorem. Given L of phi defined like this, like this, with boundary conditions that phi or a phi plus b gradient phi is equals 0 on the boundary of omega. The eigenvalue problem L of phi equals lambda of phi has infinitely many eigenvalues, real eigenvalues. All real. They have a smallest eigenvalue, but not a largest one, so that's unbounded from above. If different eigenfunctions are in have different eigenvalues, then they will be orthogonal. So if phi and phi are eigenfunctions with different eigenvalues, then they're orthogonal. And most importantly, for the space of eigenfunctions spans in space. All right, so given this theorem, let's just take it as a true fact, then we can actually complete this construction of a solution, right? Because in our case, L of phi is just a Laplacian, right? So then P is just 1, Q is 0, and sigma is 1, yeah? Orthogonality means the following. So it's exactly the higher dimensional analog of orthogonality of functions from the real line, right? So given eigenfunctions let's say phi and m, let's just use this notation, sine of n pi x over L, sine of m pi y over L, like this. If we have, say, n0, m0 are not equal to m1, m1, then if we do the double integral over the rectangle, in fact, whatever the domain is, let's say 0, yeah. This is equal to 0, and this is not particularly hard to verify in this case, because again, you can just break down this integral, at least in the case of the rectangle, into integral in x and integral in y, and then you're just having these separate one-dimensional integrals where you already know the orthogonality, so this shouldn't be a surprise. The real power that we need is that this space spans the entire space of functions. So you remember when I talked about in the early days of, well, in the early days of sending images via computer, one of the standards was JPEG, and all JPEG was doing was simply taking a picture file and thinking about it as being a function from a rectangle into the real numbers, where the number indicates the color. So if you make things even simpler and just make the number indicate a grayscale, so higher numbers are darker and lower numbers are whiter, right? Then to encode that information, what was done was simply to write the linear combination of functions of this kind that represent this function from the rectangle into the real numbers, and then cut it off at a certain point. And when you cut it off, then you have something that is meaningful if you cut it off, even when it's like the first 1,000 terms, the first 10,000, the first 50,000. you'll still have something you can recognize as a picture. It'll be more blocking than it'll be more pixelated. The lower, the less numbers you have, where you cut off the series that represent it. If you cut off the coefficients at the first 1,000 as opposed to the first 10,000, you'll have a more blocked picture. But nevertheless, you'll have something recognizable, and that is how you can send pictures through the internet, where you have a variable amount of data that can be sent in various directions and still get the thing that you want in some form to the person who wants to see it. That is how all streaming works. Now there's slightly more sophisticated ways of encoding pictures, but morally it's exactly the same thing. It's just a slightly different basis. Instead of having a basis like this, there's a slightly more refined basis that's better for encoding pictures because of various properties that pictures have as a sets of data. But yeah, it's one of the basic applications of this kind of mathematics to your daily life. These are the natural things used to encode things. When we were doing calculus 2, we learned about doing Taylor series and representing functions by an infinite polynomial power series, having the coefficients give you more and more data the more terms you include, right? The first 2 terms just a tangent line and you build up. Perhaps counterintuitively, the Taylor series isn't the best way to represent functions. The best way to represent functions is with these things, with waves, with frequencies, and the more you do mathematics, the more you realize that this is the better way to write functions, to represent functions as a sequence, and it doesn't do it in a kind of building up. So Taylor series are like building up from the local information outwards, whereas this isn't doing that at all. So it's like a less natural thing. It's less easy for us to grasp, but this is that writing things as linear combinations of frequencies is a reasonable way to represent them. But if you actually work in maths, applied maths, or theoretical physics, or in fact anything that uses a lot of math, that's what you'll find to your surprise, is that many things just are a lot better when you represent them as linear combinations of frequencies. A lot of things, a lot of calculations, a lot of principles, a lot of higher level principles become very transparent when it's put into that context. It's really kind of odd. It's like if there was an alien universe or an alien life form that could think in terms of frequencies instead of thinking in terms of lines and curves as representing functions, then that life force would have a better grasp on the universe entirely, because the math universe wants us to understand functions as linear combinations of frequencies, and that's what you'll see the deeper you get into this stuff. All right, cool. So this is all we need to conclude our construction of a solution, right? Because we saw that the only thing left for us to be able to do was to solve the following thing. We want to be able to find coefficients a mn such that these guys are equal to this, and we had a c square root of lambda m n b n m phi n m x comma y g of x comma y, right? If we could do this, if we can find these numbers a n m and b n m, then we're all set, and we can actually do this. In fact, we have these guys are easily orthogonal, so we can explicitly find out what they are. We do the same stuff we've done multiple times, except now we're going to take the inner product with respect to a double integral over the rectangle. So we're going to define f of g to be the double integral, so 0 to L, 0 to h, of f of x comma y, g of x comma y, dy dx. Okay, this is exactly the higher dimensional analog of integrating on a line. Yeah? And that itself is exactly the natural analog of doing the dot product, which is just taking the coefficients of the vector, say a and b. The dot product is just dot product of vectors a and b is just a1, b1, a2, b2, so on up to an, bn. So the inner product when we do the integral of an interval is just replacing a sum over a finite number with an integral over interval, and it's exactly the same thing. I mean, integration, as you know, is just high dimensional generalization, or the generalization of addition when we're adding over things on an interval as opposed to just a discrete set. And this too is exactly the analog for the same reason. So that this should seem natural as an inner product on the space of functions from the rectangle into R. And with this stuff, we just do this, right? So let's take the inner product of f with one of our guys, one of our eigenfunctions. By orthogonality, this has to be a m, phi m, n. Okay, and that gives us an explicit formula for what these guys have to be. And then the same thing for this thing, right? So yeah, and that gives us an explicit formula for b, m, n, and that's it. That's all we need to do to actually solve this. Yeah? Okay, some final comments on this. So let's take one of the building blocks of our solution, which is built out of our eigenfunction. So we're going to have something like this. We're going to have for some coefficient a and m, cosine of lambda m n constant c times t, and then this guy phi m n x comma y plus some other coefficient b m n sine of the square root lambda m n c times t, and then phi n m x comma y, right? Where this guy phi m n is this kind of thing, sine n pi x over L sine of m pi y over h. So what is happening to this thing? Let's draw this. So we have that we're going from 0 to L, and we are cutting L into n individual pieces, right? So if we go from 0 to L over n, if we stick in L over n into this, we get sine of pi, which is 0, if we go to like 2L over n and put this into this, we're going to get 2 pi, which are going to be 0. So cutting this line, cutting the horizontal line into n equal pieces, we have these lines like this, where this thing will always be 0, right? Should be straight line, obviously. And then similarly for the y direction, if we cut this into m, so m can be completely different from n. M could be much bigger, could be smaller, whatever. So let's draw it so it's somewhat different. Let's take m to be like 3 or something. It's not particularly good, but okay. So this is h over m, and this is 2h over m, like this. And on these lines, this thing is always equal to 0, right? So the cosine is oscillating between -1 and 1. So in each of these pieces, it could be either be positive or negative, and as the time acts on it, then the positive will gradually turn into the negative and vice versa. So think of this as like lifting off and then being pushed down to 0 and then pushing out the opposite way and then lifting off again. So each one of these little squares is kind of like pulsing up and down, right? And then these lines remain constant, and these are what we call nodal lines. So when they're actually 0, the points where phi and m are 0 are called nodal lines. Yeah. So if we can construct a drum with this rectangular outside and we hit it in such a way that we only see one frequency as the solution, and we put some sand on this, then exactly as this vibrating plate experiment would show, the lines of the sand would hit these, would flow to the nodal lines where it's not actually vibrating, and would see this kind of cross hatch thing like this. You know? Cool. So let's take a special case. Suppose L is equal to 2h, like this. This is h, and this is 2h. Then the claim is that we have totally different eigenvalues. So we have totally different eigenfunctions for the same eigenvalue. So let us take lambda of 2, 2. So what is lambda of 2, 2? Well, this is pi. Pi, this is 2 times pi times pi over L, but L is 2h squared times 2 times pi over h squared, and that becomes so that just becomes, put it over here, 5 pi over h squared, or 5 pi squared over h squared. And let us take lambda 4, 1. So what will that be? That'll be 4 pi over 2 h squared plus pi over h squared, and again that is going to be 5 pi squared over h squared. So this is an example of same eigenvalue with different eigenfunctions, and they are indeed completely different. So we have a more complicated scenario happening in this situation. All right, that's it for today, or that's it for this class. Have a good day.